Hello everyone, I'm Yaru. Today I'm going to present our work at AMOS 2021, Multi-Agent Graph Attention Communication and Teaming. This work is done with Rohan Pleasure and my advisor Matthew Gamboy. There has been recent success in multi-agent reinforced learning for games such as StarCraft and Dota. Reinforced learning is becoming a powerful technique to multi-agent systems. And communication is a basic form of swarm intelligence. If we can take advantage of the communication mechanism when training agents to cooperate and perform a task, and integrate communication in a multi-agent reinforced learning framework, it would be great. So here comes the problem. How can we make the agents communicate effectively and efficiently? High-performing communication requires reasoning about when to communicate, whom to communicate with, and how to process the communication messages. For many previous works on communication-based multi-agent reinforced learning, they failed to model the topology of communication between agents explicitly and elaborately. So, with these motivations, we propose a novel communication protocol for multi-agent reinforced learning, where a scheduler can help decide when to communicate and whom to communicate with, and to explicitly model the topology of agents' communication and reach a more powerful communication mechanism. The scheduler can learn multiple hierarchical communication graphs to support multi-rounds of communication. And the message processor in our framework can decide how to process the received messages for each agent. Before we dive into our method, I would like to go through a few preliminaries. The first one is partially observable markup game. A markup game is the multi-agent version of Markov decision process. A partially observable markup games of n agents can be defined by a set of global state, a set of local observations for each agent, a set of actions for each agent, and the transition function. At each time step, agent I will choose an action, obtains a reward as a function of the state and its action, and receive a local observation. Agent I aims to maximize its discounted total reward, where the gamma is a discounted factor. Our work is based on the framework of partially observable markup game augmented with communication. Then is policy gradients. The policy gradient, which is shown in the equation here, is widely used in reinforced learning tasks to perform gradient ascent on the agent policy parameters data to optimize the total discounted reward. The rho pi here is the state distribution. Pi theta here is the policy distribution. And RT is the discounted total reward. In practice, instead of RT, we use the advantage function, where VST is the value function to decrease the variance of the estimated policy gradient. In graph neural networks, each GNN layer computes a node representation by message passing, where each node aggregates the feature vectors from its neighboring nodes in a graph at the previous layer. So the updated rule for node representations by a vanilla GNN layer is displayed in this equation. Here, HIL represents the features of node I at layer L. Ni is the set of neighboring nodes of node I. Di is the degree of node I. WL is a learnable weight matrix for layer L. And sigma is a nonlinear linear activation function. It can be ReLU. Okay. Then let's take a look at our method. This is our communication framework. First, each agent will receive a local observation. The observation vector will go through an LSTM cell so we can get the hidden states. Then the hidden states will be encoded as the initial message for the later scheduler and message processor. Then we come to the scheduler. The initial messages will be fed into the scheduler. First, go through graph attention networks, which is a variant of graph neural networks to get embeddings which represent each agent's local information. Using these embeddings, we can get the features for interactions between agents. And then it will generate a communication graph that tells which agent should send messages to which at each time step. We also support generating different graphs for multi-rounds. And then, using the communication graphs generated by the scheduler, our message processor employs the graph attention networks to process the received messages for each agent and aggregate them intelligently in a multi-round manner, so that in the end, each agent can get a final message that can help with their decisions. Okay, we integrate this communication protocol into a multi-threaded synchronized multi-agent policy gradient framework for end-to-end training. And here is the loss function. As you can see, we optimize the discounted total reward with policy gradient and also minimize the squared error between the estimated value and the Monte Carlo estimate. The two loss functions are balanced by a coefficient beta. Okay, then we evaluate our method in three domains. The first one is the predator-prey environment. Here, there are multiple predators with limited visions searching for a stationary prey in a great world. The predators can take actions up, down, left, right, or stay. We use the average steps taken in an episode to find the prey to evaluate the performance of each method. Our approach magic can converge faster than all the baselines, and the agents can reach the prey within the least steps. The second domain we use is Traffic Junction. This environment is composed of intersecting routes and cars, which are agents, with limited visions. This scenario requires communication to avoid collisions between agents. And still, our method can converge faster and reach higher success rate of no collisions in an episode than all the baselines. As the number of agents increases, we can beat the baselines by a wider margin. The last domain we used is Google Research Football. Google Research Football is a physics-based 3D soccer simulator for reinforcement learning. This domain presents an additional challenge because there are opponent artificial agents, increasing the complexity of the state action space. Here we demonstrate 3 versus 2 scenario where there are 3 attackers, 1 defender, and 1 goalkeeper. From the chart results, we can see that Magic can reach the highest scoring success rate. We also tested our method without the scheduler, and we can see that a scheduler provides performance improvement, indicating that determining when and whom to communicate is important. And our method is interpretable. We generate communication heat maps in the predator-prey 10-agent scenario, and we average the learned communication graphs over a period of time. The horizontal numbers represent the message senders, and the vertical ones are the message receivers. The color bar represents the probability to communicate. At time step 23, the first agent, which is agent 5, will catch the prey. We can see that before the prey found, or the first catch, The communication is very intensive, but after that, it becomes much more sparse, and all the other agents can reach the prey in a short time. So this shows that our method enables agents to communicate only when beneficial and communicate efficiently. To quantitatively evaluate the communication efficiency, we use the performance improvement with communication divided by the communication graph density at some specific time step. The table shows the results in predicate 3 agents environment for each baseline and our methods. And we can see that our method magic has the best efficiency. In conclusion, we developed a novel graph attention communication protocol for multi-agent reinforcement learning with the scheduler to learn multiple communication graphs to solve the when and whom problems, with the message processor to solve the how problem. We outperform prior methods across 3 domains while communicating more efficiently. Our results set a new state-of-the-art in communication-based multi-agent reinforcement learning. At last, we demonstrate our algorithm on physical robots in a 3 versus 2 soccer scenario on Robotarium testbed at Georgia Tech. Thank you for listening. If you have any question, I'll be happy to answer them.